So geographic routing, it's using location rather than network topology to find, for packets to find their way through the network. Based on geometry, it's only using local information. So there's no node that has a global view of the entire network. Geographic routing protocols generally come in two types: a greedy distance routing protocol, where the node or the neighbor node closest to the destination is chosen. The other type is compass routing. One really isn't much better than the other. There are scenarios where one may succeed where the other fails, but there are just as many scenarios where vice versa, one will fail where the other succeeds. Plus, compass routing requires some amount of trigonometry. I don't know how much floating point support, floating point trigonometric support is going to be existing in actual chips. We could probably get away with it on the simulator. So because of that, I just chose to do the greedy distance routing. Again, it's limited because it's using only the local information. There's no global view of the entire network. If you did have an entire global view of the network, you'd probably use something like Dijkstra's algorithm to find the shortest path through the network. Here's a view of the software hierarchy of all the different components. We're using Ubuntu that Craig gave us. It's just a Linux distribution. On top of that, Python is running. TOSSIM runs inside of Python, and the configuration and scenarios that Xueying put together are running within that Python environment as well. Within TOSSIM, TinyOS is running, or at least some version of TinyOS, and then our routing program runs on a single node, actually on each of them on various different nodes within the TinyOS environment. General design overview of what the routing software does. It gets its configuration from packets which are injected. We didn't want to have to deal with some localization methods. We just wanted to have them magically know where they were and then worry about routing through that. So one of the packets that it takes is a configuration packet. The nodes, once they get their configuration, will start to broadcast their location and their node IDs to their neighbors. A neighbor counts as anyone who's connected. And then routable packets get injected into a node and then find their way using the routing protocol to their geographic destination. The node closest to the destination is the node chosen. This is the packet type. We started out using the radio count to LEDs application that Craig was using as a demonstration, and then we just modified the packet structure from there. It has a message type to indicate whether it's a configuration, a neighbor announcement, or a routable packet. The X and Y coordinates get reused in a couple of different ways depending on what type of packet it is. If it's a configuration, it tells you where you are. If it's a neighbor announcement, it tells you where the neighbor who's making the announcement is. The payload is just, we're using it right now as just an identifier. The way we're using things, it requires packets to be uniquely identified, and so basically the whole payload identifies the packet. The whole payload here is a 32-bit int, so there's not a lot to it. And then the node ID, that gets reused in a number of different ways. For the configuration, it tells you what node you are. For the neighbor announcement, it tells you for the neighbor announcement, it tells you what node it's coming from, and also for routing packets, it's telling you where it's coming from so that you know you don't send back to that. Internally, we keep track of all of the different neighbors that we hear from. Again, neighbors are just any node which you have some kind of communication with, and so whenever you hear of a neighbor announcement, you're going to make a new entry in this neighbor structure, or the neighbor array. It keeps track of what node ID, the X and Y coordinates, and the last time it's heard of. If it's not heard of in a certain amount of time, I don't remember what it was, it's probably 32 divided by 4, it's probably 8 seconds. If it hadn't heard from a neighbor within 8 seconds, it drops that neighbor until it hears from it again. Also keeping track of what I call the track, so where a packet has come from and where we've sent it to. So every time we get a new packet from somewhere or we send a packet out, we make an entry into here to say that a particular packet, we have payload ID, but a particular packet has either come from or gone to a particular node. And again, if this information ages out, I think if we haven't heard anything on this node within the last 8 seconds, we remove it.
On Python, we add 24 nodes, such like this. There is no node on 21. We define the maximum distance for a node is 2, so node 1 can communicate with node 2, 3, 6, 7, 11, but it cannot communicate with 8. Then we know the starting node and the destination.
Just a question. How do you define the communication range?
The communication range is, it's arbitrarily defined, but we're basically saying we set a link between two nodes.
Okay.
Based on the scenario 1, we add some link. We add some barriers. The barriers are created by remove the link, so the node 1 cannot communicate with 11. Our protocol can work in this route, but because of using only local information, barrier may will fail. In this scenario, it will fail. Here is how we make the configuring information. We give the packet the message type, X coordinate, Y coordinate, node ID, and destination and the time to deliver it. And here is the way how we built a noise model. Without a noise model, the communication doesn't work. Okay, let me show how to run this scenario. We define the start at node 1. The destination is 5. So obviously, based on the graphical, the best path is from node 1 to 6 to 11 to 16. Then there is no neighbors for 16 is nearest than 16 itself. So that's the path. How to transfer. At first, we built the node and the noise model and the link between each other. Then we write.
Before you do that, let me just say a couple of things. So we have nodes giving out some information. So this is all coming back through debug channels. And it's saying that here it's received a message. It's of message type 1, which means it's the configuration message. So it's telling node ID 22 that it's X coordinate and a Y coordinate, and likewise with 23 and so on. So
then I write. I want to make sure every node knows their neighbors.
So This is debug. This is 6. Node 6 is saying these are the neighbors it knows about. It knows about 7. Knows about 1, 8, 12, 2, and 11. You'll see similar information for all of the other nodes. Yeah.
Yeah. Now let's start the routing. One is the destination. File is one is the start node. File is the destination. 45 is the payload.
Number 1 is scanning its neighbors. It's saying that node 6 is closer. It's not already in the track. It compares against 7, not closer. 2, 3, 11, not 11 is closer, and it chooses to send to 11. Goes to 11. We'll see when it shows up in 11. Eventually. I hope. Sometimes either because of radio noise.
Yes.
Here we go. So again, it's got a message type 3. That's a routable message. It's still going to 5.5. 7 is closer. 12 is closer. 17 is closer. 17's not in the tracks. 16 is closer, and so it's sent to 16. 16 picks it up. It scans. 22 is closer. It's not in the tracks, but it's close enough, and says that we've got a success. 5 is reached at 4.5. It's within the distance of 2.
Yeah, that's all.
And that's it.